All right, how is everybody doing? Are you alive?
No.
No, wow. But you must be, since you all responded so very quickly. But no, why aren't you alive? What's wrong? Tired? Why so tired?
It's a final.
Have a final already?
We have final projects, all the homework.
Yeah.
We just throw on you last minute.
It's too much. It's just too much. Let's just quit. Let's just stop here. Stop now. I know it's a lot. So as part of that, you've seen there's homework that's been posted. Did you look at the assignments? They're little assignments. Little tiny bite-sized assignments. Yeah, they're like homework snacks in a way. You could sit down, watch a little Netflix, do a little physics homework. You know, just be kind of nice. No? Doesn't work that way? Rewatch something you've seen before, you know, just put it on in the background and enjoy some physics homework. Maybe we should do that while I talk. I should put on just reruns of something, kind of on the side. And you can take your pick, me or it. What do you want to watch? See, you're not even sure what it would be if we did that. What could we all agree on? A physics reality TV show.
Yeah, where we learn physics.
It's like the opposite related class.
This way we can watch it at home.
You can watch it at home. It's recording right now.
No, but I need like you in it.
You need me in it.
Yeah.
There. You can't see the screen, but I'm in it now. Is that good?
Yeah, I did the facial expressions.
Okay, facial expressions. Huh. How could I work that in? Should have just like a little box down in the corner. Just a camera on my face going, you know, making facial expressions. We have so much left to do. And I don't want there to be so much left to do because I don't want you all to have to learn it. And I don't want to have to do it all because, like, it's still a lot. But there's also a lot that I'm going to not do. So, you know, there's several slides in the remainder of this chapter that's just like, nah, let's just not worry about that. And some stuff I was planning to explain that I'm just going to be like, give you the equation and move on with life. So it's a little bit of this, a little bit of that. So hopefully we'll survive maybe a little bit. Does anybody remember this at all?
Yes.
Right hand rule? Yes, you do remember right hand rule? Yeah. Fingers in the direction, excuse me, yes, you're right. Thumb in the direction of the current. Fingers give you the direction of the magnetic field around that wire. That works for a straight wire. It turns out it works for like little segments of wires that might not be straight as well, as we'll see today. We have this one equation so far that tells us the value or the magnitude of the magnetic field a certain distance away from a wire that has current passing through it, okay? We're going to extend this quite a bit today, but before we do that, let's see, we worked several of these problems. I wanted to do this one as a bit of a practice. It ties together this new concept with our right-hand rule from the last chapter as well. It's a two-step problem. Take a minute, talk to each other, use your right hand, and try to figure it out. Can we take a vote?
Yeah.
Number 1, 2, 3, 4, 5. Like 5 people voted, I think. What about the rest of you? How about this? Let's start with the magnetic field. We need to figure out what kind of magnetic field this thing is moving through. Otherwise, we don't know what kind of force it's going to be, right? So point our thumb in the direction of this current, and then you can imagine that the magnetic field is going to wrap around the wire like this, okay? So over here on the left side of the wire, the magnetic field is pointing towards you, okay? It comes out of the screen here. In front of the wire, it's pointing to the right. And then over here, it's going into the screen and so forth, okay? So at the location of this particular charge, what did we just say? We said the magnetic field points out of the screen, and that symbol denotes out towards you, okay? So let's see. We could also write in here on this side of the wire, it's pointing into the screen, okay? Good so far? All right. Now the different right-hand rule for the direction of the force, remember it's Q times V cross B. So we start with our fingers in the direction of the velocity of the charge, and then orient our hands so that our fingers will turn toward the direction of the magnetic field. So I have to go this way, and then my fingers turn in the direction of the magnetic field. Notice which direction my thumb is pointing. To the right. Toward the wire, that's the positive X direction. So with the current going this way and with the charge going directly next to it, it's going to feel a force that makes it turn toward the wire, all right? So our answer here is positive X. Do we need to do that again?
The second part.
The second part. So let's see, for this part, we're using FB equals QV cross B. So this is fingers, this is turn fingers, and then this one is thumb, all right? So the velocity is pointing straight up, fingers this way, the magnetic field is pointing toward you, so my thumb points to the right, okay? You can do this, right, right, left, right, maybe, okay? Let's think about this in a little more detail. What if I had 2 wires that are next to each other, right? Things are getting a little complicated because you can imagine, like if there's just like no wire down here at the start, this wire with a current passing through it is creating a magnetic field everywhere around it. And you can see they've drawn in some of the magnetic field. Make sure that agrees with your right hand rule. Thumb is this way, which means above the wire, the magnetic field will be pointing at you, and underneath the wire, it should be pointing away from you. Okay, so you can see that that agrees with our right-hand rule. Well, that means if I have another wire nearby, and there's charge flowing through the wire, then this wire is sitting in that wire's magnetic field. Uh-oh, okay? So you can imagine that this wire is going to feel a force from that wire. Okay, charges are moving through a magnetic field. But I could think about that the other way around as well, right? This wire, since it has current flowing through it, is producing a magnetic field too, right? Where does it, what's its magnetic field look like? Same sort of thing. Above it, it should be pointing towards you, and below it, it should be pointing away from you. So let's draw in, let's see, some more of these. So this is the magnetic field, let's call it B2, and this one at the top is B1. So this one is creating a magnetic field around it we call B1, and this one is creating a magnetic field around it called B2. Just keep in mind, it's not just right around it, it's everywhere around it. It just gets weaker the farther you get away. So each one of these wires is sitting inside the magnetic field that's being created by the other wire, which means they are going to exert a force on each other, okay? It is a Newton's third law situation, it's an equal and opposite force. If one exerts a force on the one, the other one exerts a force in the opposite direction on it. And we've got an equation for this that I'm just going to give you because of time, and then we're going to talk about the direction of these. So the force between these charges of either one of them actually is equal to mu naught over 2 pi d. This is the distance between the wires, times the current in one wire, times the current in the other wire, times the length of the wires. And I'm assuming that there's the same length in this particular case because all of them are drawn that way. Why not? Okay? So just like we saw before, if you have a wire that current is going to pass through and you happen to be putting that in the region of a magnetic field, you have to consider the mechanical problem that a force could be exerted on that wire and it could get pulled or broken or damaged in some way. If I have two wires, both of which are carrying current and they're going to be relatively near each other, their magnetic fields interact and they exert forces on each other. So it's another thing to consider mechanically because it could cause problems in a circuit. Now let's see if we agree with what's happening over here. Notice at the top, we're going to see what the forces are if the currents are going in the same direction. They've decided that the two wires are going to be drawn toward each other. Does that make sense with our right-hand rule? We can think through it. Your question first.
After you explain this.
You sure?
Yeah.
Okay. All right. So let's start with the top one, that's the same as this one over here. So let's go ahead and use that. Remember when we're dealing with the force on a wire that's carrying current, we start with our fingers in the direction of the current and then let our fingers turn toward the direction of the magnetic field. Thumb tells the direction of the wire. So let's see, what are we going to do with this? So the current is going this direction, but it's sitting in a magnetic field that's into the screen. Okay, so that way for the current, fingers curl this way. The force on this bottom wire is up. Now if you're saying, why did you use that magnetic field? Because this is the magnetic field that it's creating. It's like, can it be affected by its own magnetic field? That doesn't really make a whole lot of sense. It's being affected because it sits in the magnetic field that's being created by the other wire, okay? So here we have current this way, magnetic field into the screen. Gives me a force up. What about at the top? That time I have a current that's this direction, and it's sitting above this bottom wire, which means it's dealing with a magnetic field that points towards you, which gives me a force down. So over in this case, the two wires are experiencing equal and opposite direction forces toward each other. All right? Yeah? More right-hand rule practice, right? What about this one? Notice they've kind of specified a little better which magnetic field we're talking about. So for the bottom wire, now we're going to let the current go this direction. It's in this magnetic field that's into the screen that's being produced by that wire. So we've got current this way, magnetic field away from you, the force is down. Same sort of thing up here. We end up with forces in opposite directions, but equal magnitudes. The wires push themselves apart, okay? Your questions get answered a little bit? Yeah, okay. If you want to ask, let me know. Yes?
What is L again?
L is the length of the wire.
What if they're different wires?
What if what?
What if they're different lengths?
If they are different lengths, then we would need to specify which force we're talking about. For instance, a force on the second wire, we would use the length of the second wire, and vice versa. Anyone else? Okay, so I just answered that question, so we don't need to do that. Skip over that. We're actually not going to do this. Isn't this fun? Don't you love it? Which brings us to something you're going to love, because it's going to be a bit of a throwback to something else you loved. You might start to be guessing. Like right now, you're racking your brain thinking, like, what did I hate the most this semester? I bet that's what he's calling back to. What was it?
Yes.
Whoa, impressive. You hated Gauss's law. Well, Ampere's law is kind of similar, but easier, okay? It works kind of the same way. We're not going to go into it in nearly as much depth, and it turns out the integrals and everything about it is just kind of simpler to deal with because we're going to be working with lines instead of areas, Okay, so it's like we take the dimensions down a little bit, it gets a little bit simpler. Okay, Ampere's law is a way to find the magnetic field from currents in symmetrical situations. So we can find B from currents in symmetrical situations. And Ampere's law looks like this, and it's going to look a little bit familiar. On this side, we have a closed integral of B dot dl. This is what's known as a closed path integral. dl is just a little bit of a path we're going to integrate around. On the right-hand side, we have mu naught, which is our permeability of free space, times the current enclosed. And this is the current enclosed by the path. There's the equation. We're going to talk about it a good bit. We're going to do two examples, and then it's going to end up in another place as well where we kind of get to practice it, but by that point we'll be talking about something else. Closed path integral B dot dl is equal to mu naught times I enclosed. So you can see in the figure here at the middle, we have a situation very much like what we just learned about in the first slide of this chapter. A straight wire with current passing through it creates a magnetic field. I'm going to show you that we can use Ampere's law to get that equation that we had on the first slide, the one that I put in a box just a few minutes ago. Okay, so I gave you the equation, now I'm going to show you where it comes from, which is Ampere's law. So you will notice that they have decided to draw a little path that goes around the current, okay, around the wire that's containing the current. So that path just forms a circle of radius r that sort of wraps around the thing that's creating the magnetic field. We know that at a constant distance away from the wire, everywhere on that path should have the exact same value for the magnetic field. We know that from the equation from before, plus it just sort of makes sense. If as long as you're the same distance from the thing making the magnetic field, you should have the same value for the magnetic field. So let me show you how this works using Ampere's law to calculate this particular situation. So let's evaluate it for that. Everywhere along the path, we can say that the magnetic field is constant, so I'm going to take it out of the integral. So I have just integral of dl. And on the right side, the current enclosed by the path, literally you look at how much current is inside that loop, inside that circle. And looking back at the diagram, it looks like the only current that's anywhere inside there is the current I. So the current enclosed is I. So we just write I. That's not too bad so far. Okay? So what is this integral dl? Here's the way to think about it. If we go back around here, each one of these little arrows might represent dl. dl just means a little bit of the path. Okay? So each one of these is dl, and each one of these is dl. If I add up all of those and go all the way around the circle, all I've done is found the circumference of a circle. So before we were doing like surface areas and stuff. This time it's literally just how long is the path. Here, if my path is a circle, the distance around the circle is the circumference, which means that this integral dl is just 2 times pi times r, the circumference of a circle. So this is the length of path. So I have b times 2 pi r equals mu naught times I. And we can calculate b from that, and we get mu naught over 2 pi times I over r, which is the equation we had before. Okay? They're not really going to get much harder than that when it comes to Ampere's law. The key things are, what is the path integral? You have to figure out, am I dealing with a circle? Am I dealing with a square? Am I dealing with a straight line? How long is the path? Figure out what that length is. And on the right side, just how much current lives inside that path. Is there one wire that has current I? Is there two wires that have current I? Is there 6 wires that are inside that path? Is there one wire that has current 6I? Like whatever lives inside that path is what you put on the right-hand side. But to help illustrate that, let's do another example, which I have a couple of slides over here. We're actually not going to do this. You don't have to worry about that one. And find the magnetic field inside a wire and outside a wire, okay? So the outside a wire part, well, that's easy. I just found that. B is equal to mu naught over 2 pi times I over R. There, that was done. The inside a wire is what's going to take a little more effort. Inside a wire, what are we going to do? So you'll notice in this diagram over at the right, for outside a wire, they used this path on the outside, which is identical to what we just did. For inside the wire, we're going to use this little path on the inside that is just some radius r that's less than the radius of the wire itself, just so that you're inside the wire. So you can see that little r here is this radius of the path. Big R is the radius of the wire itself. So we're going to say that r is less than big R, the radius of the wire. And then we're going to write down Ampere's law. So B dot dl is equal to mu naught over I, or mu naught times I enclosed. B is constant everywhere on that path. And once again, the integral of dl is just the circumference of a circle. And it's 2 pi little r because that's the radius of that little circle on the inside. The more difficult part comes with trying to figure out how much of the current lives inside that inner circle. Well, all of the current is I, which passes through like this entire wire. I've only got part of it instead of all of it. I've got a fraction of the total current. The way we can express that is by taking the total current and multiplying by a fraction of, or let's say the ratio of how much surface area I'm enclosing to how much total surface area there is. So we could write that as something like pi r squared over pi big R squared, okay? This is the cross-sectional area of the entire wire. This is the cross-sectional area of the enclosed part. So if I encapsulated the whole thing, this would just be 1 and I would have current. If I have half of it, this will come out to be 0.5 and so forth, okay? It's just a fraction, it's just a ratio. So let's see, we can solve this for B. So let's do that. Let me make sure I didn't leave anything out. I did not. Those pi's are going to cancel. Pi's canceling. I don't like the sound of that. Pi's should never cancel, ever, unless you canceled them with your belly. Never mind. It's weird. That's the second class today I've talked about pi's. And this morning we weren't talking about this at all. Huh. Pies are good. I like pies. Pies of any kind. Pizza pies, chocolate pie, pecan pie.
Pumpkin.
Not a big fan of pumpkin pie. Sweet potato pie?
Never heard of this.
Yeah, I could do that before I'd do pumpkin pie. But that's just me. What have I left out here? I'm trying to talk about pi and do algebra at the same time. Mu naught I r squared over 2 pi little r big R squared. I think that's everything. So let's see. This R cancels with one of those, which leaves me with mu naught I R over 2 pi big R squared. So as long as I know this distance from the center of the wire, I've got an equation for the magnetic field at that distance from the center, as long as I'm inside the wire. As soon as we jump to outside the wire, then we have the other equation. okay, because I've got all of the current enclosed. That's Ampere's law number 2. Shorter than Gauss's law. Can you handle it? If you could like 50% handle Gauss's law, you can 100% handle Ampere's law. Okay, that's kind of the ratio of their difficulties. I don't know. All right. Which brings me to the next thing, which is starting to, I guess, name some specific configurations of things that produce magnetic fields. So I want to give you this one just because it's quite common. You'll probably use it in the lab if you haven't already, which is known as the solenoid, which is really just, we'll say, multiple loops of wire. And you can see it illustrated here down below. It's like they just took a wire and wrapped it into a circle over and over and over and over and over again before the wire comes back out of itself again, all right? What this serves to do is it produces a strong, reinforced magnetic field inside the coil of wire and a relatively weak magnetic field outside the coil of wire. You end up with a very strong magnetic field down the center and a relatively weak magnetic field comparatively on the outside. And it turns out if you just look at the magnetic field lines on the left, we could say that it produces a magnetic field that looks a whole lot like a bar magnet. A bar magnet has a north and a south pole where the magnetic field leaves the north end where it's really strong at that end and it enters the south end. You can see that illustrated above. This is the north end of the solenoid and this is the south end of the solenoid, and the magnetic field is directed from south to north inside the coil itself. So it's kind of like an artificial bar magnet, if you want to think about it that way. One that I can tune to get the exact magnetic field that I want, depending on how much current I decide to put into the coil. All right. I should let you know something about an alternate right-hand rule here that will help with loops of wire, whether it be one loop or many loops, okay? And in this particular case, since we're dealing with something that's looping, use the looping part of your hand. Your fingers can curl, right, to correspond with the thing that's actually turning the problem. Previously, we had a straight wire with a turning magnetic field, so the magnetic field went with the part that turns. Here, I have a current that's turning, so what I'm going to do is orient my hand in the direction so that my fingers point the way the current is going. So you can see that this goes in, and then that wire is supposed to kind of come out at you and wrap around like this. That's the direction that the current is looping, like that. Notice my thumb points in the direction of the magnetic field in the center of the loop, in the center of the coil of wire. All the way down the middle of this, the magnetic field is pointing to the right. So you can see current goes like that, and my thumb points this direction. So let's write out those steps. Let's see. Fingers curl with the current, and thumb gives the direction of B in the center of the loop, coil, or solenoid. So that would work if it's just one circle of wire, perfectly fine. Or if I have a bunch of loops of wire on top of each other, the same effect applies. Which brings us to this thing on the right. What in the world is that? All right. What someone has done is essentially, I don't know, like taken a knife to the solenoid and just went right here from this direction. It's almost like they sliced through the solenoid along the screen itself and then like peeled away the front half of it so that now we're just sort of looking at the cross-sectional areas of the wires at the top and the cross-sectional areas of the wires at the bottom. Can you see that maybe a little bit? Okay. So if that's true and the current goes up like this and then it wraps around that way and in this way, well, that means for all these top wires, the current is coming at you, and then it wraps around and goes into all the bottom wires. Do you see how that corresponds to this? Okay? So we're basically just looking at a slice straight down the center of the solenoid. So from this, we can use Ampere's law, and I just want to show you this to kind of give you an idea of the versatility of Ampere's law, because this is so very different, a different application than what we saw on the previous slides. We're going to use Ampere's law to try to figure out what this value of the magnetic field is in the middle of the solenoid. And it turns out that this is a really straightforward calculation. So this time, my loop, or path, is this purple box that has 4 sides. 1, 2, 3, 4. You see them labeled, okay? And it turns out we're trying to find the magnetic field along path 1 specifically, all right? So let's work through this just really quickly. We're going to say B dot dl is equal to mu naught times I enclosed. And we're just enclosing part of the solenoid instead of the whole thing. So you can see inside here I've got this wire and 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 this, and this. I've got all of these wires. Each one contains current I. It's the same current, yes, but all of them are passing through this path that we've described with Ampere's law. Okay, so here's what we're going to do. First of all, out here along path 3, B is essentially 0. So I don't have to worry about that part of the path. Okay, along path 4 and path 2, take a quick look at the direction of these paths. So first of all, the magnetic field, or excuse me, the current is pointing towards you and the path is going this direction. It turns out that essentially along these 2 paths, B is, let's say, really small. I wouldn't say 0, but it is really small both there and there. Which means that it's really only along path 1 where I have significant magnetic field. So it's the only thing that I'm going to use in the equation. So we'll say here we have B times the integral dl, and dl is path 1 only. The others are insignificant in the calculation because there's very little magnetic field along those parts of the path. And this is equal to mu naught times I enclosed. And instead of actually counting how many I have there, it was arbitrary how many I decided to include. So I'm just going to say it's capital N times the current I. It could have been 10, could have been 15, really doesn't matter, however many I decided to put into the equation. And then this length L, notice it's just the length of this particular side of the wire. So I'm just going to call that L. It's the length of one side of the loop. So I've got BL is equal to mu naught in I. And then we can solve that for B. So B is equal to mu naught in I over L. And then I'm going to make one other little simplification and combine those two things. B is equal to mu naught little n times I, where little n is the number of loops of wire per length. This is kind of like a loop density. So if I happen to know the entire length of the solenoid and how many times it wraps around, I could divide those two, and it's like telling me how many loops per length I have. It's how tightly packed the loops are, okay? This particular equation gives me the magnetic field down the middle of a solenoid. As long as I know the number of loops, the length of the solenoid, the current that's passing through it, we can find the strength of the magnetic field.
So when you go from the integral dl and you change that to just L, that L is a constant, like the, and it's the distance from the solenoid to the center of the solenoid?
It is, for what we analyzed here, it's the distance from this point to this point. It's the length of that path. We're sort of abstracting it in this case because I could have used that exact length and the exact number of currents that were in there, or we could zoom that out and say, let's use the whole length and all of the loops of wire, and the density should be the same, whether I use a little bit of it or a lot of it, okay? So I would expect you to be able to do a little bit with Ampere's law. It's not going to be one of those things where it's like a problem on the exam. I expect you to kind of know the concept and the idea. Maybe we have to answer a multiple choice, but no more than that. And as far as solenoids, you can just straight up use this equation to find the magnetic field down the middle. I just wanted to show you that, well, Ampere's law can be used for other shapes besides just circles. All right, it can be used for boxes as well. So that's the magnetic field that's inside a solenoid. A toroid, we're not going to do, so we'll skip over that. Which brings me to the Biot-Savart law, which is probably the hardest part of this chapter. Oh. So before we do that, donuts. We're talking about pies. Earlier class today, I talked about pies and donuts. I need to know where to get a good donut around here. Help. Where? Who? Bob's Donuts? That really sounds like you made it up. No? Just Bob's Donuts. Where's Bob's Donuts? I mean, I can find out, but is it nearby? Like, could I get one, like, soon? Can I get one within 5 minutes of this class ending? Huh? I want good donuts. What do they got?
It's a donut.
It's a donut? I don't like the sound of that at all. Krispy Kreme's not far? I kind of grew up with Krispy Kreme. I feel like an advanced past Krispy Kreme. I wanted to explore the donut world that is out there. Yeah? That looks good. That looks great. How come there's like big donut and that little thing next to it? Is that somebody else's donut? Or that's a regular donut compared to a Bob's donut?
Yeah.
So Bob's donut is kind of like a donut pie. I like where this is going. Huh. By the way, I had an idea this morning. Tell me if this sounds good. I'm just stalling for the Biot-Savart law, trying to give you a chance to wake up and recover from Ampere's law before we do this. Okay, here's what's my idea. We were talking about donuts. And for whatever reason, the example I had, we had to smash the donuts and turn them into pancakes. Just don't worry about it. It was about moment of inertia. It applied. Don't worry. So imagine you took a donut, smashed it out so it was like a solid disc, like a pancake. But then you served them as pancakes, right? You made a stack of those, put maple syrup over it. What do you think? Do we have any? It's too much? Too much what? Yeah, people like too much. I'm not saying we have to eat it. Will people buy it? Someone will buy it. Like, we don't have to go over the top and put like whipped cream on it and everything.
The way you put donuts, you have to fry them.
Yeah.
It's like deep fried.
So
Pancake, it's pan fried. It's different.
It's supposed to be a little different. So it's basically going to be like deep fried pancakes.
Ooh. Why don't we just
Like
like
a fritter?
pancakes? Deep fry them simple because it's like that.
Well, that's another way to go at it. But then you wouldn't have the donutiness, right? Because then you've got the surface area of the donoid. Donoid? What am I saying? What you might think is what we have here. Basically, we have this. We have a toroid, right? That has all this surface area that gets fried. If we did the pancake, and fried it, then there's less fried surface area. And I'm thinking, if you're saying it's too much, what we need to do with the donuts is not like a really, really sweet donut. It needs to be kind of like a plain, lightly glazed donut. And then we're going to flatten those guys out. Stack them up. Okay, never mind.
So you want to take a pre-made donut and squish it?
I don't want, no, we're going to make the donuts. I don't want a pre-made donut. I want somebody like at a bakery, like a real
like
donut bakery.
After the baker makes the donut.
You're actually going to make a donut and then smash it
Yeah.
and then stack them up.
Are we glazing them?
lightly.
Before or after we make it into pancakes?
I think before we make it into a pancake.
I'm thinking afterwards, that way the pancakes can be glazed. It'd be interesting.
Maple glaze.
I'm okay with maple glaze.
Yeah.
Yeah,
We can add bacon to it.
there definitely should be bacon on the side at least. Stack of donut pancakes with a side of bacon.
Still haven't tried the Mexican food, so.
No, I haven't yet. Huh.
We should open up right next to the hospital so when everyone has a heart attack.
Yeah. Maybe that's a business in and of itself. It's like joint this thing plus urgent care. Like, two sides of the same thing. I don't know. This is all a terrible idea. Just a terrible idea. Biot-Savart law. All right, prepare yourself for this. You remember back when we were talking about electric fields? We did Gauss's law, but we also did another way of calculating the electric field from more complicated situations. I don't remember what that equation looked like exactly off the top of my head now that I'm talking about it. But we had you can use Gauss's law, or you can do this other stuff, and it's a little harder, but it allows you to solve any situation that's thrown at you. That is essentially what the Biot-Savart law is. It is for finding the magnetic field from a wire in any situation. So the wire could be straight, it could be bent, it could be curved, it could be a loop, it could literally be anything. And this will allow you to calculate the magnetic field from that wire. Let's see, so what does this look like? I am going to give you the equation, we're going to do one example, and that is about all we'll do with the Biot-Savart law. So it looks like this. dB is equal to mu naught I over 4 pi times dl cross r hat. Yes, I'm just making up stuff at this point. Divided by r squared. At least it feels that way. I'm going to have to describe several parts of this equation to get across what the idea is. Mu naught I over 4 pi times dl cross r hat over r squared. So if I want to find the total magnetic field, you have to take that particular equation and integrate it, which sounds like the worst idea ever. All right? So the Biot-Savart law, that thing at the top, is giving me a little bit of magnetic field that's coming from a little bit of wire that has some of the current passing through it. So in other words, look at this diagram at the top. Let me step through this. There is a wire here. It's got a current in it. And you can see it's like a slightly curvy bent wire, which means I can't just use the equation for a straight wire. You might imagine that I could break up this wire into little segments like they did here, which we're going to call DL. So there's a little bit DL, and here's a little bit DL, and so forth. Every little DL of the wire produces some magnetic field. So if I were to want to go, say, out to this point P and find the total magnetic field at that point from all of this wire, I need to figure out how much this little piece, DL, is giving magnetic field up there, and how much this little piece is adding to the magnetic field, and this little piece, and so forth. Every little piece of wire carrying a current contributes to the total magnetic field at that one point. You have to add up all of those little magnetic fields and get the total, and the way we do that is by integrating. This equation tells me the little bit of magnetic field created at point P from every little piece of the wire. Okay? Do I need to say that again or maybe write that down? This equation tells me every little piece of magnetic field at point P from every little piece of the wire that's carrying current, right? So the other thing that we need to look at in here is, what is this R hat? R hat is a unit vector. that points from DL, a little piece of the wire, to point P, where we are finding the magnetic field. It's a unit vector that points from the little piece of wire we're currently looking at out to the place where we're trying to find the magnetic field. R hat is equal to what? It is equal to the R vector divided by R. Well, what in the world is that? The R vector is a vector that points in the R hat direction, the same direction, from the little piece of wire out to point P, with a length of distance R. This is the distance from DL to point P. Ugh, that was a lot of stuff. R hat is a unit vector that points from the little piece of wire out to point P. And it is defined as R vector, which is a vector that points in that same direction but has a distance or a length that is how far away from that segment of wire you are. And R is literally what that distance is. So essentially we're taking this full vector, dividing out the distance, which leaves me with just a vector that points in that direction but has a magnitude of 1, which is what a unit vector is. Okay? And then we have this cross product, and you may remember that a cross product is the magnitude of those two things. So DL times R times the sine of the angle between them. Is there a lot of stuff in this equation? Yes. Is it complicated? A little bit. I'm sorry. That's why we're going to do an example. I think the example will feel a little bit familiar from things we've done in the past. So let's use this on this particular example. I don't think this diagram is the best because you have to actually read the text to see what it is. Notice it says it's a current loop, but just at first glance, looking at this thing on the side, it looks like just a bar. But if I were to turn this around and look at it from this side, there's actually a circle of wire here that has current passing through it. And you can see at the bottom, the current is going in, and then it goes around, and at the top, the current is coming at you. Okay, so imagine there is a circle that's perpendicular to the screen, and we're trying to go from the center of that loop of wire along the x-axis, and we're going to try to find the magnetic field out at some point. Okay, so if you think about it, every little piece of that current loop that's in a circle, every little piece of it is contributing to the magnetic field at that point. Every little piece of that current is giving me a little bit of magnetic field. So you could take this loop and break it up into little DLs. So if I were to flip this around and look at it from the front view, maybe it looks something like this. We have a little DL, and every little one of these is a DL, and you get the idea. And so forth, okay? This is the front view of this particular loop of wire. Do you see the diagram, first of all? Does it make a little bit of sense? Can you see what's happening there? Okay. So before we actually use the Biot-Savart law, let's try to figure out something about the direction of the magnetic field. And we're going to start by using this diagram by just looking at a little piece of the current at the top. Okay. So imagine there's a little bit of current at the top that's pointing directly at you, and you want to figure out the direction of the magnetic field over here. Using the right-hand rule, we have enough information to do that. And yeah, the answer's on the screen, but perhaps we can come to some agreement as to which way that points. So take your thumb and point it in the direction of the magnetic, or of the current right at the top. And again, we're just looking at this little piece at the top, so small that it might as well be straight. A tiny little straight wire, okay? Thumb in the direction of that current, which means that the magnetic field is going to go around like this, okay? which if I were to draw that, oh, there's not enough room. You might imagine that it makes like a big circle that looks something like that, where the magnetic field is pointing in that direction. Okay? That is the magnetic field that's just coming from that little tiny piece of straight wire right at the top of the current loop. Do you see that? Okay, again, finger or thumb in the direction of the current, and then our fingers give me the direction of the magnetic field around that little piece of wire. Okay, so out here on this center axis at point P, you can see that the direction of the magnetic field is that way. That is a little bit of the total magnetic field that's just coming from this little piece of wire. What we want to do is figure out how much magnetic field and which direction the magnetic field is from all these other little pieces of wire as we go around the circle. So you might imagine as we do that, we're going to end up with the same sort of magnetic field. It's just sort of going to like turn its way around the x-axis, like so. So if I were to break it into x components and y components, you can imagine as I go all the way around the loop, this perpendicular component, this y component, is going to start there and just sort of go all the way around, and it's going to cancel itself out, right? For every one that's up, there'll be one that's down. For one that's like right here, there's going to be one that's straight down this way. These perpendicular components are going to cancel out. But for every little piece of this wire, I'm always going to get a vector that's got a component in the positive x direction, and those are going to add up. Every single one of them gives me one of these vectors, so they're going to add up and contribute to the total magnetic field. So what we can say is that dB perpendicular cancels out, and dB parallel adds up. So this is, we'll say, adds up in the positive x direction. Right? And then we can use the Biot-Savart law. So what we're going to do is something like this. The total magnetic field is equal to the sum of all the B parallels. Yeah, that's not an 11. It's supposed to be parallel. Which is equal to the integral of dB cosine phi. And you can look back at this particular diagram and see that phi is just this angle between the direction of the magnetic field and the x-axis. And that gives me this parallel component. dB cosine phi gives me that parallel component. And then we can plug in for dB the Biot-Savart law. Okay, so that means we're going to get something that now looks like this. So now we've got the integral cosine phi mu naught I dl over 4 pi r squared. And if you're thinking, how did we just end up with dl when we had all of that other stuff before? You might remember we had, what else was up there? dl cross r hat. How did that just become dl? Well, this is dl times the magnitude of r hat times the sine of theta. Theta there is 90, so that becomes 1. The length of this thing is just 1, so that just becomes dl, okay? We evaluated that cross product, and the only thing that's left there is dl. Let me pause for a second and see if you've got questions. It's getting dark outside. What is happening? Must have been talk of all those pancake donuts, donut pancakes. Pancake donuts. I'm not sure which they should be called. I think a pancake donut would be you make pancakes and then cut holes out of the middle, and then you'd have pancake donuts. Maybe that's a thing in and of itself as well. You look intrigued by all these ideas. That's what you said? Yeah, but we're not going to deep fry them. We're going to make pancakes and cut the middle out. They're still pancakes, just in the shape of a donut. I know, it's ridiculous. All right.
We should do that for our next class.
Somebody bring them.
Bring a fryer.
Bring a fryer. I don't think we're allowed to do anything. We're not using that sink for anything. I can tell you that right now.
Oh,
Yeah, there's a sink there. Although if you look in the sink, yeah, no. You don't want to do anything food stuff related with that sink. Just not at all. Not going to happen. So let's see. What can we do with this particular thing? First of all, let's plug in for cosine phi. Question?
On the right side of the equation, that is part of that's from the last part? That's the
From
Ampere's law or no?
that is from Biot-Savart. So we're essentially using this.
Oh, so
Plugging in
that's,
for
that's,
dB.
that's a unique formula right there.
Okay. So for cosine phi, looking back at this particular diagram, cosine phi is this r, which is the radius of the loop, over the r vector, which is the vector that points from here out to the place I'm trying to measure. Okay, so we're going to substitute in for that. So that's going to be r over little r. And if we were to expand that just a little bit, we could say that that is r over the square root of x squared plus r squared. So let's write that as x squared plus r squared to the half. So we're essentially looking at this triangle and we're finding the hypotenuse. So it's the square root of x squared plus r squared. So let's plug that in and see where we stand. So now the total is equal to r over x squared plus r squared to the 1/2. And we still have this mu naught I dl over 4 pi r squared, and I forgot the integral out front. And let me see if I included everything. I think I did. So if we take a look through what's there, let's see, big R is a constant. This X is some distance that's constant away. Let's see, this big R, that's a constant. The current I is a constant, mu naught's a constant. This little r squared is a constant. The only thing I'm going to do is integrate all the way around the circle, and we're going to integrate across dl. So I can pull just about everything out of that integral. So now we've got r over x squared plus r squared to the 1/2 times mu naught I over 4 pi r squared integral dl. And again, dl is just a little piece of the circle. So if I add up all of the dl's, I'm just going to get the circumference of the circle. So this thing becomes 2 pi capital R. And don't forget, this little r here, we've already determined is x squared plus r squared to the 1/2 power. So I've got this thing squared, which is essentially just going to be x squared plus r squared to the 2/2, if you want to think about it that way. And then outside here, we've got x squared plus r squared to the 1/2. Let's fix that 1/2 because it doesn't look like a 1/2. Which means I'm going to have x squared plus r squared to the 3/2 in the denominator. And then we can cancel a few things out and see what we get. We should end up with mu naught I r squared over 2 times x squared plus r squared to the 3/2 power. Ugh. So now you can plug in different values for x, different distances along this x-axis, and this tells you the total amount of magnetic field that's coming from that one loop of wire. And yes, it takes a little bit of work to use the Biot-Savart law, which doesn't sound like a whole lot of fun. That was with a circular loop. What if it was a square? What if it was Q-shaped? I don't know. What if it was an oval? Anything that's a little more complicated than that shape is going to be a good bit more work because the integration becomes a lot harder than what we did, and that wasn't terribly easy. Actually, the integral part was easy. It was the other things, trying to figure out what to substitute in to make it easy. That was a little bit of work. okay? That's the Biot-Savart law. I think there's at least one of those in your homework to give you a little bit of practice, but hopefully I didn't assign one that was too terribly difficult. If so, let me know, all right? Because I don't want you spending forever on it. That just brings me to the last little thing I want to talk about in this chapter, and that is this slide. We're actually not going to do that. We're not going to do that, which means there's only one slide that I want to talk about, and that is magnetic materials, specifically ferromagnets, just to give you a little feel for how this works. These are materials that are somewhat naturally magnetic. And I put naturally in quotes because depending on how you find it, it might already be exhibiting a magnetic field. And if not, it turns out that I can use my own magnetic field to sort of amplify its effect and make it a better magnet. These are materials such as iron. Materials such as iron. And it turns out in materials like this, they are composed of small magnetic domains. These are little regions that are, say, on the order of 1 millimeter in size that act like little magnets. We're not going to really talk about why those little regions act like little magnets. If it helps at all and you want to look into this later, this is likely due to alignment of electron spin. Which, if you think about it, an electron is a charged particle. And although it doesn't like spin in the sense that we're thinking of, you can kind of think of electron spin as like being a little tiny loop of current. And when charges are moving, it produces magnetic field. So it's kind of like electron spin creates its own little tiny magnetic field. They just happen to all be aligned in these little 1 millimeter size regions. And that creates like little mini magnets inside the material. Well, what happens is that typically these are all in random directions. So in other words, they all cancel each other out. But I can use an external magnetic field to, we'll say, grow the domains in alignment with that external magnetic field. The ones that are already in alignment with the external field sort of start to dominate the material. And you can see this illustrated up on the top right. First of all, with no magnetic field, you just have all these little magnetic domains that are pointing all sorts of different directions. So all those magnetic fields sort of cancel each other out. But if in the second part, I create a magnetic field on the outside, so maybe I use some other apparatus to make a big magnetic field and put this material in it, notice there were some of the domains in the top diagram that were already pointing to the right, like this one and this one. You can see now those have gotten larger and sort of squashed out ones that were pointing in other random directions. So now overall, if I kind of look through this, a whole lot more of the material is now pointing to the right, which means that all of those magnetic domains aren't canceling out, and the material itself, once I take it out of the magnetic field, is creating its own magnetic field because the domains are in alignment, okay? This is essentially what is happening. No, I won't say that. No, I won't say that. Let me back up from that just a little bit. This is a physical thing. Like literally, we've created like a physical growth and alignment of structures on the inside that are now pointing in a certain direction that are all contributing to an external magnetic field and making its own magnetic field, such that if I now take the material and literally just slam it against the table, I can rejumble all those things into random directions, and the thing that I turned into a magnet is now no longer one, which is kind of weird. It's like I can take this invisible thing, right, a magnetic field, and make stuff line up inside the material. I can't see any of that happening, but now it's like, ooh, this thing is a magnet, and then I can mechanically re-jostle all that microscopic stuff and make it all cancel back out again. I don't know, it's kind of a cool sort of thing, all right? So that's the basic idea of magnetic materials, and it's also the end of chapter 30, which is kind of nice, all right? Chapter 31, I'm not gonna start it, all right? Here's what I wanna say about what's coming up. We have Thursday, and then we have Tuesday, and then we have Thursday, and then a week after that, on Thursday, we have the final exam. I can't be here for the final exam, so next Thursday, that's our last class together. We'll all say, have a nice life, and that'll be kind of fun and stuff. Someone will be proctoring the exam simply because, I'll just go ahead and tell you, my wife works at the hospital. It turns out she has off the week before Christmas and has to work all of Christmas week, including Christmas Day and everything. So if we're gonna see family at all over the holidays, that was the only possible week where we could travel or whatever. So alas, I'll be sitting home alone on Christmas Day as my wife works. But you can feel a little better because you took the exam here without me and allowed me to like go on a little trip before the holidays. So that'll all kind of work out. That said, I don't know if we're gonna have time for a review with the material that we have left. And even if we did review, it would be so short and rushed through everything that I don't even know if it would be helpful necessarily. Anything would be helpful. I'm going to do what I can. We have chapter 31 that we have to fully cover. 32 is kind of like we sort of cover it. 33 we barely even do. I just need to kind of tell you some of the things that are in there. So it's kind of like these remaining chapters we're going to cover less and less. I think there's enough time to do them on Thursday and Tuesday, which would leave a review on Thursday, but we'll see what happens. Wait, your question first and then back here. What's that?
Are we able to do like whatever you want?
A review online. What would I do?
Study guide.
Study guides. What is a study guide? I'm confused by study guides.
It tells you exactly what's on
What's exactly on the test is like all these lecture slides and notes. I don't know. I'm confused. A short
It's focused.
I'm confused by. So what you want is the exam.
Yes, yes.
I would prefer that, but if not to do that, it's not.
What was your question? Let me think about this.
I was gonna ask about, are you gonna give us like a study guide?
We want study guides.
How long is the exam?
That would be our Christmas gift.
It has to exist first. I don't know. I don't know how long the exam
I
is.
said you cancel the exam completely.
Just cancel it completely.
I
I don't know. Let's see what happens Tuesday or Thursday and Tuesday, and then we can figure things out for a review on Thursday. And let me decide what to tell you about the exam, how long it's going to be, and whether there's materials I can give you to practice and/or a study guide or something. We'll sort all that out. At this point, I have no ideas, so we'll see. So we'll end there 6 minutes early. Goodbye. Enjoy the dark world that is outside. Eat a donut for me. Or smash it first, and then eat it and tell me what it tastes like after you smash it. I'm just going to keep talking to myself because it's fun.
Probably still tastes like a donut.
It probably does, but the texture is going to be a little different maybe. I don't know, maybe it'd be interesting.
But isn't half the goodness of a donut being all the air inside?
It's a good
It
point.
would just be a really dense donut.
Yeah. Maybe that'd be good though. Because with all that air, you could probably compress it down quite a lot, and then it'd be like a donut bite, like a donut shot. You get the whole donut, like in one bite. Whew, that sounds rough. Yes.
Will you email me?
I will email you. Let me give some thought as to, you suggested next Tuesday. I assume you didn't mean today, but next Tuesday.
I can do it if you want.
If there's anything you can do later this week, that might be
Thursday or
better.
Friday.
Okay. Let me give it some thought and I'll respond to you. Okay.
Yeah.
My
Yes.
friend wants to know if you have any sessions next semester.
I do not.
Okay.
No.
Okay, well, it's still there. It's still there. I'm
Do I
trying
know
to.
that later on, as in future semesters, or I don't know about that yet?
Okay.
Typically, for the fall semester, I would probably know something late spring.
Well, yeah, I haven't
At the
done
earliest.
anything with it. So I was like, oh,
Thank you.
Mhm.
I got this. So I'm like,
I figured it's more beneficial for me to actually.
Yeah, I mean, if you have the time.